Welcome to the day 2 of Unit 1 notes. A lot of this is going to sound familiar from what we did in Unit 0, so this should go relatively quickly. My plan is to go through the day 2 notes, but then also start a little bit of day 3. All right, so we're just going to go through some definitions of things in geometry that we're going to use a lot. Namely, we're going to start with things relating to points, lines, and planes. A point is a location that has neither length nor width. So as you see over here, I have the geometric figure point A. It's labeled simply point A. Now, a line is an infinite set of points that extend infinitely in both directions. A line has no width. There is exactly one line that can be drawn through any 2 points. So if you have 2 points A and B and you connect them with all the points in between and beyond, that creates line AB. Now you can do it as capital A, capital B with what appears to be a line symbol above it. Okay, that's literally the line notation. It looks like a line. Or BA. Order does not matter, but capital letters to denote those points and the line bar above it. Now we also can label lines with a single letter. Typically we do lowercase letters for that if we label the line itself, not the points on it. So this is just simply saying, oh, that's line M, is how we would phrase that. Now collinear means points of the same line. And I like to tell my students to think of co as in like your co-workers, meaning with, co-workers, people you work with. Collinear means points within the same line, linear. So collinear points would be, if I gave these like letters A, B, and C, those are collinear because I can draw a single line between or through all of them. Non-collinear would look like this over here where no straight line would go through it. It would have to curve, and that's not a line then. Now a plane is a flat surface made up of points that extend infinitely in all directions. There is exactly one plane through any 3 non-collinear points, and points of the same plane are called coplanar. So collinear, points of the same line, coplanar, points of the same plane. This is typically how we denote what a plane looks like. It looks like a parallelogram. There's your 3 collinear points that would make, or non-collinear, points that would make that plane. And it extends out forever. I usually tell students to think of planes as like the surface of your desk. That's a plane. And then there's points within that plane that are contained. And then you can also create lines and line segments and rays, etc. within that plane. The intersection of 2 or more geometric figures is the set of points that they have in common. That's called our intersection. So if you have lines P and S intersect at point T, that's your point of intersection. You could also have a line intersect a plane at a specific point. So you have line M intersecting plane Q. Okay, now just like last unit, we'll talk about line segments. That's the measurable part of a line containing 2 endpoints and all the points in between. Okay, so you'll notice it doesn't extend through with the arrow because the arrow denotes going on forever. It simply ends at A and B. So your notation is capital A, capital B with the segment bar above it, or BA. Order doesn't matter. Now, as soon as I say capital A, capital B with no line segment listed, now this is the length of that line segment. So just jumping even to this example, AB equals, that's saying what's the length or the distance between A to B? And that would be 5. What's the distance from B to C? What's the distance from A to C, which in this case it would be 5 plus 3, which is 8. So the length of a line segment AB is the distance from A to B and is denoted as AB or with the little absolute value bars. Honestly, 9 times out of 10, you're just going to see capital A, capital B. Now, the idea that I did in the previous part here, where I just did part plus part equals whole, the way I was able to do 5 plus 3 equals 8 is a geometric theorem called the whole is equal to the sum of its parts. So, in my diagram over here, I have point M, which is between P and Q. If M is between P and Q, then this could be a part, this could be a part, and if I add them together, that would give me the whole line segment. Kind of makes sense, right? And that's what's being described right here. So if PM equals 6 and MQ equals 4, using the idea the whole is equal to the sum of its parts, part plus part equals whole, I know the distance from P to Q would be 10 units. All right, we didn't talk about this last unit, but you should recognize this from middle school. A ray is part of a line with one endpoint and all the points extending away from that endpoint in a given direction. This would be the notation A, B, C. Okay, the endpoint in the next ray is CBA, so I'm going to start with C, endpoints at C, and then draw the arrow to the right because everything's extending towards A. Sometimes students say, well, can I just rewrite it and have the arrow go to the left? And the answer is no. We will always write our notation where the arrow is going to the right. And that's how we name our rays. All right, last vocab word here is geometric figure, and this is just the set of points in the same plane. So for example, figure ABC is contained in plane P. ABC would be a geometric figure. More specifically, it's a triangle. All right, just practicing some notation here. If I ask you to find CF, that is saying what's the distance from C to F. So if I look on my number line, that looks like 5 units of distance. So I'll write 5. What's the distance from A to B? Now notice that it's in the negative side of the number line, but when we talk about distance, distance has to be positive. So we're going to write 2. So again, it's not negative 2 because distance can't be negative. All right, for 3, BC plus CE. Well, I'm finding that BC is equal to 1 unit. CE looks like it's 4 units. So BC plus CE would be the same thing as 1 plus 4, and that would give me 5. Now, the justification for why I'm able to say this part plus this part would give me this whole is the sum is equal to, oh, I'm sorry, I'm writing that wrong. The whole is equal to the sum of its parts. All right, lastly, a little true or false. AB equals FD. AB appears to be 2 units, because right here we found that earlier. FD is also 2 units. Since they are the same distance, this would be a true statement. All right, so that concludes the end of our notes for day 2, which are super short. Okay, so I'm at 9 minutes in my video right now. A lot of this you've already seen before at some point, whether it be in unit 0 or just whether it's something you learned when you were in middle school and they talked about geometry. Okay, so nothing should have been too terribly earth-shattering here. This statement that I just used, the whole is equal to the sum of its parts, is a statement that we'll use a lot when we get into something called formal proofs. And that's something that you've never seen before, but everything else should be relatively familiar. Now, since this is a pretty short day, I'm actually going to teach a little bit more into day 3. Just like in day 2, a lot of this will sound familiar as well. The word congruent. When we talk with segments, congruent means same size and shape, and your congruent symbol is an equal sign with a little squiggly above it. if we know that AB and CD, the line segments, have the same distance, that means that they must be congruent to each other. Look at my notation. This is saying the line segment AB is congruent to the line segment CD. A midpoint is a point between the two endpoints of a line segment that divides a segment into two congruent segments. Each segment will then be equal to half of the original length. So if we know M is the midpoint of PQ, then I know that PM is congruent to MQ. I also know that PM, which is this part right here, will equal half of the whole, which is PQ. Likewise for MQ. This statement right here, a midpoint divides a segment into two congruent segments, will also be used a lot in the coming units. So keep that in the front of your brains. We'll use that one a lot. A segment bisector is any line, segment, ray, or plane that intersects a segment at its midpoint. So over here, if this is line L and maybe this is line segment AB, L would be your segment bisector, where it's intersecting the segment at its midpoint. So I'm going to write off to the side here. Maybe I'll even highlight this. That's your segment bisector. L bisects AB, so therefore M is the midpoint of AB. And we talked about that in Unit 0 as well. All right, so what is the difference between intersects and bisects? Because this is really important to know. If I say that line P intersects RS at point X, like this diagram shows, that means X could be anywhere on this line segment. But as soon as I change it to line P bisects RS at point X, that means that X specifically has to be a midpoint, and a midpoint divides a segment into two congruent segments. Okay, so if line P intersects at point X, X isn't necessarily the midpoint of RS. It could be, but we wouldn't have enough information to make that determination at this point. But if I say bisects, as I told you last unit, when you hear the word bisects, I want you to informally think cuts in half. In order to have something be cut in half, that means it needs to be intersecting at the midpoint. So in this specific case, X must be the midpoint of RS. So Rx would then be congruent to XS because a midpoint divides a segment into two congruent segments. In fact, I'll even add that right here. Okay. So let's put this into practice. If I have line K intersects line M, line K intersects line segment AB at point M. By saying intersects, all I know is that M is between A and B. Okay, I cannot conclude that it's a midpoint. It just says intersects it, so M could be anything. If M is between A and B, then it must be true that AM plus MB equals AB, aka the whole is equal to the sum of its parts. All right, so let's say that AM is 2 and BM is x squared. I also tell you that AB is x plus 14. That's the whole distance. And I want to find the value of x. I can set up my equation by saying part plus part equals whole, or x squared plus 2 equals x plus 14. Now, before I solve it, you'll notice there's a justification on the right-hand side. So this is where I'm going to get really nitty-gritty with you, and I need you to explain why you knew to set up the equation that you did. And this is what's leading us into proofs in the coming unit. So justifying why you knew to do that. I knew that M was between A and B, so I could do part plus part equals whole. So my justification would be the whole is equal to the sum of its parts. Okay, now to solve, just like what we did on day 1, I can set this equal to 0 by doing x squared minus x minus 12 equals 0. And then a little AM factoring. So factors of negative 12 that sum to negative 4 or negative 1 would be negative 4 and positive 3. And I'm getting x to equal 4 and x to equal negative 3. Now both of these solutions would work, meaning they don't cause any distances to be negative, because if you plug a negative 3 back in for x here, the whole distance would still be a positive 11, so that's fine. Likewise, a negative 3 squared is a positive 9, so your distance is still positive, so that checks. So this actually has 2 solutions. Okay, now you're going to see this change when I say line K bisects line segment AB. If line K bisects it, again, cuts in half, that means that M must be the midpoint. If I could spell midpoint. Of AB. So therefore, AM must equal MB. Those distances must be the same, or those line segments must be congruent. So if I tell you that AM is 3x plus 25 and MB is 5x plus 17, I can solve for x and find the length of AB by using this conclusion right here. Okay? Now, in order to solve for x, should be pretty obvious here that if these two segments are congruent, to solve for x, I can just set 3x plus 25 equal to 5x plus 17. Now, why did I know to do that? This is where it goes back to what it means to have a segment bisector, okay? Because I didn't tell you to set those equal. You had to infer that based on the definition of a segment bisector. So for step 1, to justify being able to set these equal, I'm first going to define the segment bisector because that's where the problem started. A segment bisector intersects a segment at its midpoint. Okay? So that's what allowed me to figure out that this point M was the midpoint because I had a segment bisector. Okay, cool. Now you know that M is the bisector. Why would you know then to set those two parts equal? Well, because we know a midpoint divides a segment into two congruent segments, and that's your second justification. All right. Now, if I go back to solving, I could subtract the 3x. I'd still have to subtract the 17, so what is that? 8. So x equals 4. All right, so this is a good place for me to stop. Oh, actually, before I do, this problem actually wants me to find the length of AB, so AB would equal 2 of whichever side I really pick. Maybe I'll pick 3x plus 25. So that's 2 times 12 plus 25. 2 times, what is that? 37. So 74. Okay, sorry. Almost forgot about that. Okay, so technically in this problem, we had to solve for AB. I almost forgot. So make sure you reread your directions for the problem. Anyway, so like I was saying, this is a good place for us to stop. Like I said, I wanted to teach a little bit ahead in the next day because I still have about 2.5 more pages to go, and we'll touch upon a little bit of constructions. Okay, so your assignment is to finish up 2A-2, and if you want to start taking a look at 2A-3, since I started the day 3 notes, that's fine too, but you only have to do 2A-2.